Hi everybody. Another couple of requested problems. So from section 3.2, number 38. And this idea tends to be a bit confusing generally until you get to the idea of what do you do with this if. So if I was working with the number -2, I would actually be talking about it here because of the or equals. It's a boundary, so we do need to see what it's doing in this one just because it's a boundary. But generally, if I said 4 falls in this category, we're talking about this function. If I say -6, well, -6 falls in this category because it's less than -2, so we use this function. The -2 is that boundary, and that's our potential point of confusion. So here's what we do. Let's start with the boundary. If I take -2 and I plug it into its appropriate function, I get down here, oops, I just did it. So -2 times a -2 minus 3. I don't know why I keep putting that in parentheses. So that becomes a 4 minus 3, which is a 1. So at the ordered pair, -2, 1, because it includes the -2, I'm going to put a solid dot there. Now I do need to know what the other line is doing at the boundary, so we're going to put -2 in here, even though it's not included in that graph, or that portion of the graph. So I've got -2 plus 1, which is -1. To indicate that I don't get to use it, I put a hollow dot there. It's the boundary. So at -2, -1, I've got a hollow dot. Now I could be at -2.1, and that will be included. So that's what that hollow dot is indicating. That we can creep really close to it, but just can't be at that value. And I just need to know where that line is going, so that's why I dealt with the boundary there. Now, I'll take a -3, and since -3 is less than -2, I plug it in here. -3 plus 1 is -2, so I go -3, -2, put a dot, draw my line. Now I need to do something to the right. So I'm going to choose 0, because 0 is easy to work with. So I have the ordered pair 0, -3. I'd have 0 down here. -3 is where it would cross. I didn't extend that down. Here's my -3. Forgive my lack of perfect scale. If I chose -1, it falls in this category. Put it here. -2 times -1 is 2. 2 minus 3 is -1, so at -1 I have -1. Another dot, draw my line. Okay, so piecewise functions are completely dictated by the restrictions in the domain. Hopefully that helps a little bit with 38. Now, in section 3.3 we had the request for number 11, and our function that we're dealing with, forgive me, I forgot to put f of t, is equal to 1 over t plus 4. And the x values are 9 and 9 plus h. Now we need y values for there, so I take 9, plug it in here, and I have 1 over 9 plus 4, or 1 over 13. I take the 9 plus h and I plug it here, and I have 1 over 13 plus h. And the slope formula will read y2 minus y1 over x2 minus x1. So y2 minus y1 over x2 minus x1. The bottom's not too bad. 9 plus h minus 9. The 9's subtract out, and we're left with h. The top's a bit of a clunky mess. So I've got to get a common denominator. I don't know what this number is, but I do know a way to get a common denominator. When I have two numbers, I can just multiply them, and that will generate my common denominator. So 13 times 13 plus h. Well, this denominator got a 13, so the top needs to get a 13. Multiply the top and the bottom by the same value. And the same idea over here, 13 plus h and 13 plus h. Now, in the numerator, I have to distribute my negative. I have a common denominator, so I just wrote it 13 plus h, and that's all over that. And then this negative needs to get distributed to both the 13 and the h. So it reads 13 minus h over 13 times 13 plus h over the h that we had in the denominator of the fraction, the big fraction. Well, really, this is h over 1, and this is negative h, and it's a copy dot flip situation. So we copy the top fraction, and we flip the second fraction, and we we multiply? Well, our h's cancel, and you're left with negative, and that is a negative. It's supposed to be a negative. Negative 1 over 13 times 13 plus h. Okay. Now, number 20, if you can look in the book, this is imperfect. So I have an approximate on the negative 1.5. I have an approximate on the negative 2.8. Same thing with the 4.3. These are abouts, okay? So the relative minimum, it's not the overall minimum, but there's a minimum in just that little region, is about at negative 1.5, negative 2.8. And a relative max, it's in the region. So the graph looks something like this. So in this region, this is the low point. That's the relative min. In this region, this is the high point. That's the relative max. Because the graph goes off to infinity and goes off to infinity, there's no actual absolute max or absolute min, but we can talk about bumps in the road or little gullies. And that's okay to deal with. So those are called relative mins and relative max. Relative max happens at about 2, the x value of 2, and its height is about 4.3. Now, the decreasing part is anything that's going downhill from left to right. And so the graph is going downhill from negative infinity to about negative 1.5. That's the x value. And we're uniting that with from 2 off to infinity. So we're dealing with this region here, and we're dealing with this region here when we're talking about it decreasing. And then increasing is going from 1.5 to 2. So we're talking about this section in the graph there. We don't include the bottom and the top because at that moment, it's like if you toss a ball up in the air and you just watch it, it hangs there for a moment. For a moment, it's not going up or down. It's just holding there. And our argument in math is that its tangent line is flat for a second, and its tangent line is flat for a second. So it's not increasing or decreasing right at that moment. Okay, I'm hoping that helps.